Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on computer science, and we are talking about the paper machine learning. In this particular module, we will be continuing with our discussion on reinforcement learning, where in this particular module we will be concentrating more on one particular type of reinforcement learning, which is called Q learning. So, the people responsible for this module are the following. This is the development team for this module, and the learning objectives of this module are: we are talking about a model based versus model free reinforcement learning, which we had touched upon in the previous case. Again, we are going to look at deterministic and non-deterministic rewards and actions. We are going to talk a little more in detail about Q learning, and then we are going to summarize what you learned. Let us now talk about policy and cumulative reward. So, we define a policy in this way. It is a pi, which is a mapping from the set of states to the set of actions, and each and every time you have an action which is taken from this mapping. Okay. So, that is called a policy, and a value of a policy V of pi of S of t. So, the value of that particular state S at time t according to the policy pi, and we have already discussed this is a finite horizon, where we assume that the agent is allowed to take some finite number of steps only. So, here we have up to t steps. So, the value of the policy of each state S at time t is nothing but the expected utility that you are expected to get for all the states that come in future, that is r t plus 1 is the reward at t plus 1 time slot, r plus 2 t plus 2, and you reach the finite state at the end, which is r t plus t. So, this is nothing but a summation of I is equal to 1. We have just touched upon this in the previous module also. I is equal to 1 to t r of t plus 1. So, this is with the finite horizon. In the infinite horizon, we assume that the time is not limited. The agent can keep on learning, doing the work and reach the state. So, it is infinity. But what we have done is we have introduced a gamma factor, which is called a discount rate, and this gamma factor is used to it is nothing but gamma I minus 1 r t plus 1. It is used to discount what will come in future. So, every reward is not given as much importance as just like that. It is given according to a discount will keep on increasing as you reach the rewards reach the infinity. So, this is the infinite horizon. That is how we are trying to handle the modeling of the infinite rate. Now, let us talk about this is the Bellman's equation, and this is an optimality equation. So, the V star of S of t is nothing but the maximum policy. Remember, we are deciding on a policy pi. What is the maximum of the policy that will give me a maximum value for S of t for all S of t, all states at t. So, you have a set of states at t, and at the set of states, which is the state that I will reach on following a policy, which will maximize that value for me. So, this is nothing but the maximum of the action, maximum that you have to take, which will give me an expected value from I is equal to 1 to infinity of that. So, this is again we are just replacing this with the equations that we spoke in the previous slide, and finally, you have a value of S of t is nothing but the maximum that you can get from S of t on taking the action a t, that is the value of the action that you will take. The Q is told when you are talking about both the state and the action. So, the value of the action that you will take in state S t. So, Q of S t a t is nothing but, we are just replacing that, is nothing but the expected value of the reward at t plus 1 plus the discounted value at t s t plus 1, the probability of reaching state t plus 1 when you are in state S t on take action a t, which will maximize that value of the state action pair at t plus 1. So, this is the cumulative reward that we talk about. Now, let us go back to the discussion on model based learning, which we had already discussed in the previous module. So, here we have an environment. We are assuming that the environment, the probability of reaching S t plus 1, that is the state t plus 1 from given S t and that is the state and the action, and we are also given the probability of the reward that you will get for the state at t plus 1 when you move, the reward you will get at t plus 1 when you are at state S t and you are taken the action a t. So, this is the environment. So, the environment is basically the reward and the state, known reward. there is no need for exploration, because you know what is that is needed, you do not have to look at unknown. So, this can be solved using dynamic programming approach, which we saw briefly in the previous module also. So, what we do actually have to do is we have to solve the value of that state ST given which will maximize the expected value given this action AT and the expected reward at RT plus 1 and the discount of all this. So, this is what you get at ST plus 1, all the states that you can reach at ST plus 1. This is what you have to solve, and the optimal policy will give you this particular value. The policy is the one that you will follow. So, the value is given, based on that value you have to follow the policy. Now, the value iteration, initially you set the value of all the states to arbitrary values, and then you repeat for all S belonging to the state and all the actions that belong to action the set A. You try to find out QSA, that is from the state on action. You try to find out what is the expected value of the reward given the state and the action plus the discounted, and then you set V of S, that is V of a state, to be whatever maximum you get on taking action A from that state S. So, that is Q of S A, and you keep doing this until V of S converges. Initially you put to arbitrary values, you keep doing this, setting the maximum value of V of S and keep doing this till V S converges. So, this is the value iteration. Then we have the policy iteration. The policy depends on the maximum value. So, you initialize a policy pi randomly. Remember, the policy is a set of that mappings. So, repeat pi is equal to pi dash, compute the values using pi by solving the nonlinear equations like this, and you try to improve the policy at each and every state. So, every state you have to try to improve the policy until there is no change in the policy. So, here the policy is completely based on what value you get using that policy, that is the only difference here. So, that is about policy, cumulative reward. How do you iteratively start with arbitrary values of value and then try to find, and then what is the policy you find, policy which is the best policy to find to get the maximum value for a state. Now, we go to temporal difference learning. So, this temporal difference learning we will again go a little more in detail in the next, but before we go we have to understand what we mean by temporal difference learning. Remember, in the previous just before we had discussed that the environment is known. Here let us assume that this particular environment, what we mean by environment, what is the state at t plus 1 given the state at t and action at t, what is the probability of a reward at t plus 1 given the state st and at, this is not known. If you are not knowing this, then this is called model free learning, that the probabilities are unknown. So, in that case we need to do exploration, because we do not know where to go. In the previous we knew how to maximize, so we knew the direction to go. So, here we do not know the direction because we do not know the probabilities. So, what we have to do is you have to sample from these probability values and use the reward received in the next time step to update the current. So, what you do is you start and then you choose a value, assume a probability, and then you try to find the reward you receive, and then you update using that reward, you update the correct state or the action. So, the temporal difference between the value of the current state and the value discounted from the next state is what is the temporal difference. So, the temporal difference is the difference between the value of the current action and the value discounted from the next state. So, exploration strategies, you have eta greedy with PR eta, choose one action at random uniformly and choose the best action with probability of 1 minus eta. With probability eta, choose one action at random uniformly and choose the best action with the probability of 1 minus eta. So, this is called an eta greedy action. So, the probabilistically you can say probability of choosing an action given a state is nothing but the expected quality q value you will get on S comma A among all the values that you will get on taking B is equal to 1 to A is the actions. Okay. So, what is the probability of A? You are given all the actions and what is the best probability. Move smooth, and you have to move smoothly from exploration to exploitation. So, for that you have to decrease the value of eta. Okay. So, choose one action at random with the probability of eta and you keep decreasing the eta. So, the number of times you will choose the action at random will decrease in that time period. So, annealing this you will get this value p of, that is the probability of choosing an action given a state is the expected value of q S comma A given t and this value. So, this is how you what is the action you will choose given the time also, total time also. So, now we talk about deterministic rewards and actions. So, here what we do is, this is Q of remember Q of STAT, that is state and action, is nothing but the expected reward at time t plus 1 plus the discounted ST plus 1, the probability of the state ST plus 1 given STAT, and the maximum action that you will take to get that Q value at ST plus 1 and AT plus 1. Remember, two things we are talking about, one is the reward and one is the state that you can reach. Now, deterministic single possible reward and next state. So, you know if you are at Q STAT, then this is the reward you will get, okay. It is not that, and you know this is the maximum value you will get. So, it is all known, you do not have to check for all the states. So, you know the single possible reward and what will be the next state, and it uses an update rule or a backup rule. So, Q cap ST comma T is R T plus 1 and the discounted value maximum of Q cap ST plus 1 AT plus 1. So, starting at 0 Q values increase, but never decrease, that is the way we have defined the values of Q. Now, let us look at this. Consider the value of an action marked by star. If path A is seen first, Q star is equal to 0.9 into maximum of 0,81. So, that is equal to 73. Then B is seen, so that is equal to 90, or if path B is seen first, you will have 90, then A is seen 90. Q values, as you can see, it goes from 73 to 90 and 90 if A is seen first, and if the A and B are shown there, and so this is the A and B, and this the discounting value is 0.9. So, Q values increase, but never decrease. Now, that is about deterministic rewards and actions. Now, we are talking about non-deterministic rewards and actions. When next states and rewards are non-deterministic, there is an either because there is an opponent who will try to stop your progress, or randomness in the environment can change. We keep averages or expected values instead of assigning values. So, that is the difference here. So, this is this part of it is called as Q learning, and this was discovered by developed by Watkins and Ian in 1992. So, what we do here is, we have a learning rate associated, where we have same equation. It's you can have two policies here. So, this part of that the marked in red, that is this part of it is what we are going to talk about. So, you have an off policy and an on policy. So, learning B is a TD learning, Sutton 1988, and where you are doing a discounted with the value function at ST plus 1 only, and that is why it is called as learning B. And now we talk about Q learning. Q learning is actually a special case of temporal difference learning, TD, and Q learning handles discounted infinite horizon MDPs. So, we know what is infinite horizon, and we know discount, we have a gamma value which keeps on the discount keeps on increasing or the reward keeps on decreasing as you go along to the infinite horizon, and it is a special the Q learning simply learns from experience. There is no model of the world. Q learning is easy to work with in practice. It is exploration insensitive, so it does not bother about the exploration aspect. Q learning is the most popular and seems to be the most effective model free algorithm for learning from delayed reinforcement. So, the reinforcement is happening after a delay. In this case, the most effective model free algorithm seems to be Q learning. However, it does not address the scaling problem, and there is a chance of it converging very slowly. So, that is the disadvantage. So, what are the basics of Q learning? At each step, what we are going to do is we are going to choose an action that will maximize the value, and Q is an estimated utility function. It tells us how good an action is given a certain state. So, Q of S comma is the immediate reward for making an action plus the best utility for the resulting state. So, this is a recursive definition, because each time you will try to choose the action that will give you the best utility Q for the resulting next state, that is the state you reach on taking action A from state S. So, what is this Q learning rule? This Q learning rule is given this way. Okay. Remember, it is a special case of temporal difference learning. So, S is the current state, S dash is the next state, A is the action, A dash is the action of the next state, R is an immediate reward, gamma is the discount factor, and q s comma a is the expected discounted reinforcement of taking action A in state S. So, this expected discounted reinforcement or taking action in state S is nothing but the expected the value initial value that you had of q s comma a plus alpha, I will talk about alpha, plus r, that is the reward, immediate reward, plus the discounted of maximum of the a dash action of the next state, q maximum of what action you will take to get the maximum q s dash comma a dash, that is the expected discount reinforcement of taking action a dash on reaching in state S minus the q of s comma a, and this s comma a comma r comma s dash is called an experience tuple, that is S is the state that you are in, A is the action you will take, R is the immediate reward that you will get, and S dash is the state that you will reach from S on taking A. And you will see that the policy associated is the one that will choose the given any state, the policy is the one that makes you choose the best action from the state such that it maximizes q of s comma a. Now, we want to choose the best action in the current state, that is what I was telling. So, let us pick the one that leads to the best next state and include an any immediate reward. So, what we are trying to do, what do you mean, what is the definition of best action? The best action is the one that will lead you to the best next state. Okay. So, this is the way in which this action value function is defined. So, this action value q of pi e s comma a is nothing but immediate reward received for going to state w s comma a plus gamma of u pi e w s comma a, the future reward from further action discounted due to the one step delay. You remember the one. So, that discount is happening because it is a one step delay, you are getting only a gamma discount. We can accurately learn q, the action value function. Choosing action is easy. Choose A where A is equal to the argument max q s comma a dash is the actions. So, what you are trying to do is you choose an A such that the q value is the maximum from S on choosing one of those actions. So, choose an A dash such that the value of q s a dash is the maximum. So, that is the A you will choose, so that you get the maximum value. So, let us look at q versus u visually. So, u is stored on the states. So, u remember u we use the utility of a state, we did not bother about the action then. So, utility of the first state is 1, utility u2 is the utility of the second state, u3 is the utility of the third state, and so on. So, that is the utility, while q is stored on the arcs and it has to do with the state and the action. So, from u1 the state 1 you can have q1 I, that is the action is called I, or 1 small one. So, from 1 the state 1 you can take action 1 and reach 2. So, that is 1, or you can take action 2 and reach 3, or action 3 and reach 4. From q1 the state 1 you can choose any of these 3, similarly from 2, 3 and so on. So, the actions are given by arcs and q's are stored on the arcs. So, this is a basic difference between where you find the utility of a state independent of the action, and here you find the utility of a state or the value of the state based on both the state and the action. So, let qt be a current estimate of the correct q. Our current policy is pi of t s a such that you are always going to choose the q of t which will maximize the qt of s b, whereas b is the known actions. So, our current utility estimate will be in this way. This is, remember, utility is always only associated with the state and not with the action. So, ut of s is equal to the qt s comma pi t of s, hence u table is embedded in the q table and we do not need to store both. So, u table is nothing but what is the state you will utility of a state is nothing but the q of the state and the policy you choose or the action that you take from S is that is that qt of S comma a in other words, but how do you choose a? The choice of a is based on the policy, where policy as we see in the previous equation, the equation on the top, that is this equation, you know that this policy is nothing but the choice of a. How do you choose that a? You choose that a such that it maximizes the q value of the destination, okay, or the action that you have taken. Now, assume we are in state ST, then you run the program for a while, meaning n steps, and you determine the actual reward and compare it to the predicted reward and adjust the prediction to reduce the error. This is normally lot of machine learning policies follow this. So, you try to determine the actual reward and compare it to what was the predicted reward, and then you try to adjust the prediction in such a way that you try to reduce the error. So, that is you follow the current policy. So, for model free reinforcement learning, instead of learning the optimal value function we directly learn we do not bother about what the value of each state or anything, we directly learn the optimal Q function, that is action that you have to take. So, recall Q S comma A is the expected value of taking action A in state S, which is what exactly is the policy we want, and then following the optimal policy thereafter. So, the optimal Q function satisfies, which gives B of S is equal to maximum of A dash, the action that you have to take from the state S. So, how can you learn the Q function directly? Given the Q function, we can act optimally by selecting the action greedily according to Q S comma A without a model. So, what is this greedy selection? You keep selecting such that you always choose the action that gives you the maximum value of Q of S comma A. So, it may not be in the long run the best, but at each and every state you choose the one that maximizes the value of Q of S comma A. Suppose you have 3 actions S comma A, S comma B and S comma C. Then you choose the one that gives you the maximum Q value. Okay. But later on it may not be the same, but that is why you say call it a greedy approach, you are going only one step. Okay. So, here you have this is the immediate reward plus beta, this is the transition from S to S dash and the value of S dash. So, this can be written as maximizing of the action that will choosing the action that will give you the maximum value of the Q, that is from state S, which is the action that you should take that gives you the maximum value. Okay. So, that is model free, and the Bellman constraints on optimal Q function is given in this way, and we perform updates after each action just like we do in temporal difference, but after taking an action A in state S and reaching state S dash, we directly observe the reward R of S. So, what we do is Q of S comma A is nothing but Q of S comma A plus alpha R of S is the reward, observed reward, plus beta, choosing an A dash which maximizes Q S dash, the destination, minus the Q of the previous state. So, sample of Q value based on the next state. Okay, that is why it is noisy. So, the value of Q depends on the value of the Q value of the next state. So, Q learning was done by Watkins in 1989, and it is actually a one step simple backup to learn action value function Q of S comma A. It is the most important reinforcement learning algorithm in use today, and it uses a one step error. What we are doing is we are finding Q S comma A, and we are putting the value of Q S of comma A depending upon the Q of S dash comma that action. So, one step error is possible. So, the error S comma A is nothing but the reward and the discounted value of the next state minus the Q value of this state. So, to define that incremental learning algorithm, we can write as delta Q S comma A is nothing but alpha into that term which is about the next maximizing the next state minus the original value of Q, and this alpha comma t follows the same schedule as we did in a temporal difference algorithm. We will go, actually we are going to go a little more in detail about the temporal difference algorithm as we go along. Now, what are the steps? Start with an initial Q function which can be all zeros, and then take action according to the explore exploit policies, should converge to a greedy policy, and perform the TD update, that is temporal difference update, where the temporal difference is nothing but the difference between the the Q factor of the destination state minus the source state. So, that is what you do, you find that. So, Q S comma A is the current estimate of the optimal Q function. Then you go back to the step 2, take action again, update it and so on. So, it does not require model since we learned Q directly, uses explicit S into A table, that is state action table to represent Q, and explore exploit policy directly uses the Q values, and you can use Boltzmann exploration example. We are not going to discuss this more in detail. So, in the Q learning algorithm, we initialize all Qs arbitrarily, any random values. For all the episodes you initialize yes, then repeat, you choose an A using policy derived from Q. Example, it could be an eta greedy, take action A, observe R and S dash, then update SA. Okay. So, update SA and then put the new value of state as S dash, and you keep doing this till you have reached a terminal state. Okay. So, this is one algorithm. Modified algorithm of this is the part of the initial part is the same. So, initialize all Q S comma A arbitrarily. For all episodes you initialize yes, choose the action using policy derived from Q, that is using the eta greedy policy. Take action A, observe R and S dash. Now, you choose an A dash using policy derived from Q. Again you choose an A dash and then update. So, here you are choosing an A dash appropriately using the eta greedy. So, there also you are bringing in the exploration. Remember, eta greedy was for exploitation problem, and then now you put S is equal to S dash and A equal to A dash till you reach the terminal state. So, value based terminal difference versus Q learning. There are different opinions to this. When state space is small, then this may not be much of an important issue. When it is very large state spaces, value based learning a model with and utility function can be difficult to learn good models for very complex environments. But if you can learn a model, then learning utility function is simpler than learning Q. So, it depends on whether you can learn the model. You can also reuse the model for related problem, that is one of the advantages. Q learning is learning a Q function. It is simpler to implement since we do not need to worry about representing and learning a model, that is a major advantage of Q function. But Q functions can be substantially more complex than utility functions, and you must make up for not having the model after all. Okay. So, if you take an example, if you want to find your way to the goal, this is an immediate value, just an immediate value, simple. Then this is the V value, value of a state, then this is the value of the Q, that is state action pair, and this is the finally finding one optimal policy. So, this is an example of how to find your way to the goal. So, this is unrealistic in many problems. What is the reward if a robot is exploring Mars and decides to take a right turn? So, you cannot define reward for that. Fortunately, we can circumvent this problem by exploring and experience how the world reacts to our actions. We need to learn R and the delta. We want a function that directly learns good state action pairs, that is the Q. What action should I take in this state? We call this as Qs comma A. Given Qs comma A, now it is trivial to execute the optimal policy without knowing R s comma A and delta s comma A. So, we have this. Okay. So, this still depends on R s comma A and delta s comma A. However, imagine the robot is exploring its environment, trying new action as it goes. So, at every step it receives some reward R, and it observes the environment change into a new state S dash for the action A. So, how can we use this to learn the model, that is S, A, S dash and R to learn the model. So, that is what we do in this step. So, the equation continually estimates Q at state S consistent with the estimate and one step in the future. So, it is one step temporal difference learning. Note that S dash is closer to goal and hence more reliable, but still an estimate only. So, as you go along, it is supposed to be more nearer the goal. Updating estimates based on other estimates is called bootstrapping. We do update after each state action pair. We are learning as we go along, or we are learning online. We are learning useful things about explored state action pairs. They are typically most useful because they are most likely to be encountered again. Okay. So, an example of this is the initial state is Si, then you take a right. Okay. So, you are here, then you take a right, you reach here. So, this is the next state S2. So, QS1 A right, that is action, is a reward plus the discounted value, normally use discounted of 0.9, maximum of Q cap S2 A dash. So, this is we assume there is no immediate reward plus discounted value 0.9, maximum of, now here you have 66, 81 and 90, 63, 81 and 90. So, you choose the maximum of this, which is 100, sorry 66, 81 and 100, you choose 100, and so you get this value to be 90. So, Q learning propagates Q estimates one step backwards. So, the exploration exploitation we have already discussed. It is very important that the agent does not simply follow the current policy when learning Q. The reason is that you may be stuck in a suboptimal solution. There may be other solution that you are unaware of because you have never seen them. So, it is better to try out new things now and then. So, that is that eta greedy that we were talking about. So, we take a idea of having an once in a way taking a random action. So, some of the improvements of this is one can trade off memory and computation by caching in on S S dash R. After a while, as Q S dash A dash has changed, you replay the update, that is possible. One can actively search for state action pairs for which Q S, comma A is expected to change, and one can, that is with some heuristics, and one can do updates along the sample path much further back than actually one step. You can even do 2 step. If you do all the steps, then it is TD learning or temporal difference. So, you can do stochastic, and you can, if the state space is too large, we can learn a function for that, and neural net with backpropagation has been quite successful for doing this. Okay. So, this is a function approximation basically, and update rule is where you do this update. So, we outline the various value iterations, policy iterations, the temporal difference learning a little bit, and exploration strategies. We explain deterministic versus non-deterministic rewards and actions, and reviewed the model based and model free reinforcement learning, and basically we discuss Q learning steps, example, and some improvements to Q learning. So, Q learning, as you remember, is a special case of temporal difference learning. We are going to go a little more into detail of temporal difference learning in the next module. So, thank you.